Hello, I am Ralph Gable of the Electronics for the Inquisitive Experimenter YouTube channel. Well, I want to have multi-band capability, but I don't have room for an extensive antenna farm. So what do? One of your options for covering multiple bands with a single antenna is what is called the trapped antenna. This video started out as purely a theoretical video on how to simulate a trapped antenna using the free 4NEC2 antenna modeling software. Then I started thinking that you might want more. You might want to actually design and build a trapped antenna. In this video, I'm going to walk through lots of practical stuff here on trapped antenna design and build. In the next video, I will show you how to use the free 4NEC2 antenna modeling program to design the antenna. I've put a link to this video up in the corner here just for you. If you have questions or comments, please feel free to add a comment to this video. I do honestly make a concerted effort to respond to every single comment. If you find this video helpful, please click on the like and don't forget to subscribe. So let's start off by describing the antenna playing field very briefly. Whenever we begin a discussion about antennas, we are entering a world with a huge number of variables, many of which cannot be mapped or appreciated by the average guy in his backyard, and certainly not by this guy. There is the size and conductivity of the wire, the height above ground, the kind and moisture levels of the ground, the surrounding buildings and topography, and, well, so very much more than all of that. All of these things affect the final impedance, the bandwidth, the radiation pattern, and efficiency of the antenna. The best that we can do is set up our simulated environment as best we can and then leave room for experimentation and adjustment when we get our antenna to the field. From here, I will be referring to what I call the bandwidth of an antenna. I want to be sure that you understand what I mean by this. As we scan an antenna for its SWR across a band of frequencies, we will see the SWR change. If it is tuned properly, the SWR will drop well below 2:1 at some point, and then will rise back up above 2:1 as we continue to move in frequency. If we take the difference between the two frequencies at which the SWR drops below 2:1 and then rises back up above 2:1, this is what I define as the bandwidth of an antenna. Well, why 2:1? Well, I needed a definitive way of defining what I meant by bandwidth, so I could compare apples to apples between every configuration and antenna I played with. This just seemed to be a nice number to choose. Well, 2:1, or roughly 11% of your reflected power. With that said, let's proceed with our trapped antenna. I'm going to be addressing the whole topic of a symmetrical trapped dipole as opposed to some of the asymmetrical designs out there. What this means is that the same stuff is going to exist on the right side as exists on the left side of the antenna. A trapped dipole antenna is a multi-band antenna which consists of two wires, one for each of the two legs, and a center feed point for the transmission line. As a dipole, its characteristic impedance will be in the vicinity of 75 ohms. Now this will go down and it loses broadside directivity as the dipole approaches the ground. It accomplishes the multi-band feat of magic through the use of traps inserted in each leg of the antenna, which modify how the feed line sees the entire antenna. Each time we add a set of traps to the antenna, we add one more primary band to our coverage. Well, what exactly are traps? Well, let's think about the idea of a trap in general. The purpose of any trap is to catch and secure something. There are all sorts of traps for all sorts of purposes, but they all have one thing in common. Once the thing to be caught is in the trap, we're not letting it loose. Now we have a similar thing happen when we're talking about antenna traps, except we're not talking about catching mice. we're catching a signal. We are preventing the higher frequency signal from escaping the confines of its shorter wire and hiding the fact that there is more to this RF world than the shorter wire knows about. We want that higher frequency signal to be content and happy in its more confined world. How does it do this magic thing? Traps consist of a parallel resonant combination of an inductor and a capacitor. Traps do their magic thing through the interaction of the ratio of their capacitance and inductance and the antenna that they're inserted into. Yes, the resonant frequency of the trap does make a difference, but not as much as you might think. Now let's talk about trap design a bit. To this end, I have done a host of virtual experiments using 4NEC2 with an 80-meter, 40-meter trapped antenna. These experiments were mainly centered around the design of the traps themselves, looking to see what makes a difference and how. So here's a compilation of my observations. First of all, let's address the resonant frequency of the trap. I was very much so surprised to see how little a difference the actual resonant frequency of the trap made. As long as it is higher than the frequency of the rest of the antenna, 80 meters in my case, and not too far above the highest frequency of the higher frequency part of the antenna, well, that's 40 meters in my case, the antenna wire lengths can be tuned to provide a usable antenna. In my experiment, I carefully maintained the same ratio, the values of the capacitor and inductor, while I created virtual traps for resonant frequencies of 7, 7.15, and 7.3 megahertz. In each case, I adjusted the wire lengths for each leg to give the best SWR at the center of the 80-meter and 40-meter bands. And here's what I noticed. First of all, the minimum SWR for each band didn't change enough to even be significant. But the bandwidth did change appreciably, especially for the 40-meter coverage. I gained 30 kilohertz of bandwidth by tuning the trap to the bottom of the band, 7 megahertz. At the same time, I lost 10 kilohertz of bandwidth from the 80-meter band. Next, let's take a look at the quality or Q of the inductor or the trap. The Q of the trap is affected by the Q of the inductor and the Q of the capacitor. The Q of the inductor is the inductive reactance divided by its series resistance at a given frequency. The Q of the capacitor is the capacitive reactance divided by its equivalent series resistance, or ESR, at a particular frequency. The higher the ESR of the capacitor, the lower its Q. Unfortunately, generally speaking, the higher the voltage rating of the capacitor, the higher its ESR. They might not even give you an ESR for a capacitor. They might give you a dissipation factor. Q is equal to 1 divided by the dissipation factor. So I was looking at a particular capacitor, and they said that the maximum dissipation factor of that capacitor was 1.5%. Now, that comes out to 0.015. So the Q of that capacitor would be 1 divided by 0.015, or 67. Now, Q operates in the same way as parallel resistors. So if our inductor has a Q of 500 and our capacitor has a Q of 67, then the resulting Q of our tuned circuit will be the Q of the inductor times the Q of the capacitor, all divided by the sum of the Qs of the inductor and capacitor. In this particular case, it would be 500 times 67 divided by the quantity 500 plus 67, which would give us an overall Q of 59. Now, 4NEC2 refers to this as the Q of the inductor. In this set of experiments, I left all of the specifics of the traps the same. The only thing I changed was the Q of the trap. I chose to test 3 different values, 10, 100, and 1000. In each case, I optimized the length of the wires in the resulting antenna system for the best SWR at the center of the respective bands. And here's what I noticed. Again, I was surprised at how little effect the Q had on the minimum SWR at Qs from 100 to 1000. As expected, the very best SWR at the resonant point of the antenna system is to be had with the higher Q inductor. With a Q of 10, the performance of the antenna system was totally unacceptable. The best SWR on the 40-meter band was 2.5 to 1. It's not hard to maintain a Q over 100 for any well-constructed inductor. Nonetheless, pay attention to this for the best performance here. Now, the bandwidth of the antenna system was virtually identical for Qs of 100 and 1000. Being that the SWR never dropped below 2 to 1 for the Q of 10, its bandwidth was pretty much irrelevant. Though I have to admit, it was pretty flat, varying from 2.5 to 1 to 3 to 1 across the entire band. Now, as I said before, what is most important is the ratio of the inductor and capacitor values. However, we have to start somewhere with a fixed capacitor value. So what do? In order to make an informed decision, one has to be aware of the effects of the choice of values. In this experiment, I maintained the resonant frequency of the trap while changing the capacitance value. Of course, this also means that the ratio of the capacitor and inductor values also changed. In this experiment, I used 2 different capacitor values, 47 picofarads and 100 picofarads, while maintaining the resonant frequency at 7.15 megahertz. In each case, I optimized the lengths of the wires associated with the antenna system to minimize the SWR at their resonant frequencies at the center of the respective bands. The minimum SWR, well, it was virtually unchanged. The choice of a capacitor value does not seem to affect this particular aspect of the design. The bandwidth was quite a different story, however. On the 80-meter band, the larger 100 picofarad capacitor provided a 50 kilohertz wider bandwidth than with the 47 picofarad capacitor. On the 40-meter band, the smaller 47 picofarad capacitor provided an 80 kilohertz wider bandwidth than with the 100 picofarad capacitor. Based on these observations, it seems that the bandwidth of the antenna system on its associated bands is a critical deciding point in the decisions with regard to the design of the trap. This will affect, first of all, the choice of the capacitor value, and second of all, the choice of resonant frequency of the trap or traps to achieve the desired bandwidth response on the bands covered by the antenna. We must also pay attention to the Q of the inductor used in the design to achieve the best possible SWR at the resonant points of the antenna system. Now, let's talk about types of traps that are out there. There are 3 basic types of traps. The first one is the parallel LC with discrete inductor and capacitor. They may be constructed in a variety of ways. One way is with a tubular capacitor at its core, which is constructed with aluminum tubing and polypropylene or other plastic tubing. This tubular capacitor has the coil mounted around it. All of the components are readily available, maybe scrap tubing from a discarded TV antenna or whatever. Now, here is one such example. It's a 14 megahertz trap that I threw together as an experiment in the shop. Another way is with the discrete coil with the commercially manufactured capacitor suspended down its center. Here is one such example. It is a 2 megahertz trap with a discrete 100 picofarad capacitor inside. Then there is the coaxial trap. This one looks like a roll of coax, but with a difference. It is connected in such a way to create a parallel LC circuit utilizing the characteristic capacitance and inductance of the coax, and the reality of its coiling is the capacitor and inductor. I have provided a link to a freeware coaxial trap calculator in the description. It will report the resulting capacitance and inductance for your simulation, but it does not report the Q. I have used this quite successfully in creating coaxial traps for various frequencies. Here is one such example. It is a 2 MHz trap made from RG58 coax. And here is another example of a 14 MHz trap. The third type of trap is a self-resonant trap. It is an inductor with a known self-resonant frequency. The capacitance is supplied by the interwinding parasitic capacitance of the coil. The combination of the inductance of the coil itself and the parasitic capacitance associated with the construction of the coil form a parallel tuned circuit with a predictable resonant frequency. I have provided a link to a calculator of sorts in the description. I have not used this yet, so I make no statement as to its veracity. I have also provided a link to the site that I got this from. My take: wind a way bigger coil than you think that you believe that you're going to need, check its self-resonant frequency, and then reduce the number of turns until you reach your desired frequency. Here is one such trap with a resonant frequency of around 10.3 MHz, which has obviously been modified from its original design. So how do we choose what kind of trap to use? Well, it's a matter of personal preference. Probably one of the easiest implementations is a trap made from coaxial cable. But this doesn't give you much control over the actual inductance and capacitance associated with the trap. The self-resonant trap suffers the same fate. By definition, the self-resonant trap tends to have a lot of inductance. Both work, and both are used extensively and successfully. My opinion is that if you want ultimate control, then a trap made with a discrete inductor and a discrete capacitor is the way to go. You can choose to create your own tubular capacitor or buy discrete commercially manufactured capacitors. Of course, temperature stability of the capacitance value might be of concern, as this will exist outside. So why should you care? Well, first, for the sake of modeling, you will need to know the capacitance and inductance values irrespective of what method you choose. The modeling program wants to know 3 things about your trap: the capacitance that you're using in your trap, the inductance that you're using in your trap, and the Q of the inductor, or the Q of the trap itself. Now, a quick leg up on building your antenna. Now that we know what we're going to build, what is the process step by step? Well, first of all, we need to build and tune the traps. Then we need to measure out the wires, but add additional length to allow for adjustment in the field. Put it all together and raise the antenna to a place where it's going to live. Because environment can significantly affect performance, we need to have the antenna in place to accurately evaluate its performance. Then we tune the inner wires first, the higher frequency. Then we tune the outer wires next, but they interact with one another, so go back and recheck the higher frequency, recheck the lower frequency, back and forth until you are satisfied with the overall performance. But how do you tune an antenna trap? Here's a quick note on how to do exactly that. To begin with, you need some basic adapters. I made this one for my vector network analyzer with an N connector and a couple clips. I made this one for my
antenna analyzer with an SO239 and a couple clips. And then just a very simple loop of wire. This is some number 12 wire that I just grabbed out of some house wiring. Next, you need to isolate your trap from the rest of the world so that all you're going to be measuring is it. You don't want it affected by your bench top or some metal or something nearby. So I have it here suspended between my workbench on one side and my workbench on the other side. And this is my 14 megahertz trap intended to upgrade a field day inverted V antenna. Using our special adapter, we connect our loop of wire to the input of our antenna analyzer, and we loosely couple it to our trap. We then can tune the frequency of the antenna analyzer and watch for a dip in the SWR. The frequency at which the SWR is at its lowest point is the resonant frequency of the trap. This is indicating almost exactly 14 megahertz. Now with the VNA, it's a similar thing. I have my loop of wire connected to my input connector, and I'm loosely coupling it. Notice that the loop of wire is at right angles to our trap and loosely coupled. So you take a look at the screen. Let's give ourselves a little more something to look at here. Whoa. Try again. I'm loosely coupled to the antenna trap. If the frequency is low, then you need to take your winds on your trap and spread them out just a little bit to decrease the inductance. If your frequency comes out high, you squish them together to increase. Notice that my resonant frequency of this is exactly 14 megahertz, which was the design frequency intended for this design.
Now you have a fairly complete picture of what a trapped antenna is all about and the kinds of things that you have to think about when you're designing one. In the next video, I will show you how to use the free 4NEC2 antenna modeling program to design this antenna. I've put a link to this video up in the corner here just for you. If you found this video helpful, please click on the like and don't forget to subscribe to the channel. Thank you so much for watching. Until next time, toodaloots.